So this is regarding light, right? Light rays. Actually, it is geometric optics. So when you're dealing with this, your geometric knowledge will be really useful. Okay. In this case, we are studying the behavior of light rays. Actually, right? Behavior of light rays. First, take down this note. Then I'll explain. Right? Uh, Write down light is an electromagnetic wave. Light is an electromagnetic wave with a small wavelength and small amplitude. Small wavelength and a small amplitude, right? So for the light rays, it is like 450 nanometers, right? The wavelength, and the amplitude also is small. The amplitude, right? Then first thing you have to understand the difference between a light ray and a light beam. Okay. So when we are thinking about light rays, normally we denote that the direction of light moves. So this is a light ray, right? So this is how we show a light ray with an arrow. You need to mark the arrow. In the exam, if this arrow is not marked, sometimes they remove marks, right? Yeah. So you have to show the direction that. So this is a light ray. Take this down. So this is a light ray, right? Then a bunch of these light rays creates a light beam. Then there are several types of light beams. If these light rays are parallel, such a light beam is called a parallel beam. Take this down, right? Parallel beam. Let's say light rays converge. So this is converging light rays to a point. So we call this a converging beam, right? Then if light rays goes out from a point, we call this divergent beam. Take those down. So you have to clearly understand these names, right? Parallel, what is a light ray, what is a light beam, right? Okay. Then write the subtopic refraction. Subtopic refraction. Okay. Okay. So what is refraction? So when you take an interface that separates two mediums. So let's say like this. This could be air, this could be water, or this could be glass, water, anything, right? Any two mediums. So this line, we call this interface. You can take notes as I'm explaining, okay? Interface. This thing we call interface. It separates two mediums. Let's say this is first medium. This is second medium. Right? A light ray can come like this and be an incident on the interface, right? On the incident. On the interface. So this ray is what we call incident ray. These names you have to remember, right? So this ray, we call that incident. Incident ray. Okay? then the point which it incidence is what we call point of incidence. This is called point of incidence, right? Then you have to draw. Whenever you think about refraction, once you do the incident ray, you must draw this perpendicular line or the normal, right? Or we call this normal. It is normal to the interface always. So whenever you draw ray diagrams, you have to mark this normal, right? We can say this normal. Okay. So through the second medium, this ray incidence here. Through the first medium also it can incident like this, but here it is being incident like this, right? Then what happens is the direction it has to move is like this, but it changes the direction like this. This is what we call refraction. So this ray is called refracted ray, right? Refracted ray. And incident angle, we call this I, that is incident angle. You may always measure these angles with the normal, right? So without drawing the normal or the perpendicular, you cannot measure this angle. You always have to measure this angle with the normal. Okay. Then refracted angle with the normal refracted ray. So we call this refracted angle. Okay. Okay. I think it is clear. You have to clearly understand these terms, right? These definitions you have to clearly understand. Right. So under normal circumstances, about 80% of energy of the incident ray gets refracted. About 20% gets reflected. This always happens, right? 20% gets reflected. So this ray is called, it is a partial reflection, right? Partial reflection, reflected ray. Okay. So whenever there is a refraction, there's always a partial reflection as well. So you have learned reflection in like O levels, right? So you know that incident angle and angle of reflection, they are equal, right? They are equal. So these are the basic principles, basic things that you need to understand under refraction. Okay. You need to name all these things. So every line has a name, right? So if you want, another thing is angle of deviation. Angle of deviation. So this ray was going to go in this direction, but it has deviated this much, right? It has deviated away from the normal. So this angle, we call that angle of deviation, right? This angle is what we call angle of deviation. So always angle of deviation is measured with this direction to the ray, right? So that is angle of deviation. So angle of incidence, refracted angle, angle for the partial reflection, and angle of deviation, right? And this point, we call that point of incidence. So to the point of incidence, before drawing ray diagrams, you always have to mark this perpendicular or the normal, right? Normal. Right. I think you have taken this down. Under this, write down reason for refraction. reason for refraction is change of speed of light, is change of speed of light. Under that, right, in rare mediums, light speed is higher. In rare mediums, light speed is higher. Then on the another line, right? In denser mediums, light speed is less, right? All over, right? So you know that when you think about air or a vacuum, light can easily go through that, right? So the light speed is higher. It is the maximum value. If medium is like glass or water, then the light speed, it decreases, right? It decreases. So that is the reason refraction happens. The speed of light changes, right? So there's a refraction that causes the light beam to bend at the interface. So that is how the refraction happens, right? Under that, right, a point in a vacuum, light speed is maximum. In a vacuum, light speed is maximum. Within brackets, right, you know this one, 3 times, this is the approximate value, right? Actual value is 2.9 something, but this is good enough, right? 3 times 10 to the power 8 meters per second. Then right, any medium relative to a vacuum, any medium relative to a vacuum is dense. Relative to a vacuum is dense. Okay, any medium relative to a vacuum is dense. So you know, any other mediums, the light speed is less, right? So those are called dense mediums. If the light speed is higher, those are called rare mediums relative to other mediums, right? Then another point, we'll quickly take notes, okay, in the point forms. Another point, in order of air, comma, water and glass, light speed decreases. Okay. To the same line, right? Hence, water is denser relative to air. Water is denser relative to air. Full stop. To the same line, right? Water is rare relative to glass. Water is rare relative to glass. Okay. So water is rare relative to glass means light speed in water is higher than light speed in glass, right? So likewise, you have to understand the difference between rare and denser, right? Okay. Then we have to talk about laws of refraction, right? There are two main laws regarding refraction. Okay. Write down the subtopic: laws of refraction. Laws of refraction. Right. Take down the first law. Number one: incident ray, comma, normal drawn to the incident point, comma, normal drawn to the incident point, normal drawn to the incident point, and refracted ray, are in a one plane, right? So that is the first thing. So whenever you draw geometric those diagrams, those diagrams are in a one plane. One plane means if we consider the board, so light ray is on the plane of the board, then the normal also is on the plane of the board, then the refracted also plane of the board. This cannot happen, right? Like if incident is like this, then the refracted ray cannot move like this, right? Out of the board. It should be on a one plane. So that's what these three things, right? These three things are in a one plane. It could be like this as well, but everything can contain in a one plane, right? Must contain in a one plane. So that is the first thing. Whenever we draw geometric under our syllabus, right? Right. Then the second one, you don't have to draw this. You understand that. If you don't, let me know. Okay, second law, right? Write down second. For a monochromatic light ray, comma, ratio between sine value of incident angle and refracted angle is a constant for the given two mediums, okay, for the given two mediums, right? You don't have to draw this, right? So let's say this is I and this is R. Let's say this is water and this is glass. It could be any two mediums. Sine value of I divided by sine value of R. This is a constant, right? It's a constant. Even if you change the angle, let's say you change this I, R increases. When you increase I, R increases. By increasing that, by changing that, this ratio is kept constant, right? This ratio is kept constant. So that is what we call Snell's law actually, right? This is what we call Snell's law, right? Okay. Done? Okay. Under this, right, hence refractive index of second medium, hence the refractive index of second medium relative to first medium relative to first medium. So let's say this is first medium, this is second medium. So that expression we can denote like this, right? This is how you write this. You have to carefully understand this. When they say refractive index of second medium, so it goes here, right? Second medium. Don't mix this. Second medium relative to first medium, right? Relative to. Here you put the relative term, right? The meaning of that is refractive index of second medium. How many times the refractive index of second medium compared to the first medium? All right. Within brackets, write this N12. You can write it like this, right? Put a comma, then write N12 is equal sine I divided by sine R. So that constant is what we call the refractive index, right? Relative to the first medium. Refractive index of second medium relative to the first medium. So we call that sine I divided by sine R. Okay. And also they have found velocity at the first medium divided by velocity at the second medium. This also is equal to the ratio between light speeds in first medium and second medium. Right. So that is how we defined Snell's law. Okay, Snell's law. Then let's consider two cases. Two cases to apply the at this side of the book you can write this one, this diagram. Let's say here you have the dense, here you have the rare, and you always have to draw this normal. Let's say the incident ray comes like this, and this angle is I, goes to the rare medium. So whenever it goes to the rare medium, it bends away from the normal. So it has to bend like this, right? Not towards the normal, away from the normal, right? It bends away from the normal. Then the another case, so let's say this is medium 1, medium 2, medium 1, medium 2. Let's say now here we have the rare medium, then the above we have the dense medium. Okay, above we have the dense medium. Then to which direction does this move? Since this is denser compared to this medium, the light ray bends towards, right? Towards, like this. It bends towards the normal. It was supposed to go like this, but it bent. It refracted, right? The refracted angle is measured always with the normal, like this. Here as well, refracted angle is like this, right? So these are the two cases. The light ray, when it goes from denser medium to a rare, it bends away from the normal. Here, goes to a rare medium to a denser medium, it bends towards the normal. It bends towards the normal, right? So at the book, you can draw this at two sides, right? Just separate the page. You can draw that at the two sides. Done. So thumbs up if you're done, right? And if you have any problem, let me know. Okay. Now, we can talk about Here, when the ray goes from denser medium to a rare medium, simple r is larger, right? Under this you can write more, it is larger than incident angle. And the speed of wave in this medium should be what? It should be less, right? In the dense medium, it is less. If it is V1, you can say it is less. In the rare medium, it is larger, right? In this case, we can write the same. Here, incident angle is larger, right? Can you see? Incident angle is larger, refracted angle is small. Then what about speeds? In the rare medium, speed is high, so it is V1. In the dense medium, speed is low, so it is V2, right? So you should be able to do this comparison, right? Okay. Then you need to think about angle of deviation, right? You have to correctly understand that. It is the deviated amount of the ray, right? So you know that this ray supposed to go like this, right? This ray is supposed to go like this. But due to the change of medium, it deviated away from the normal. So this is what we call angle of deviation, right? So when ray goes from denser medium to rare medium, you can write the angle of deviation how? So you can see if this is I, this angle should be I, right? Then angle of deviation should be what? R minus I. If you don't understand, tell me, right? R minus I. In this case, it is R minus I, right? Let's think about this case. The light ray goes supposed to go like this, but it bends towards the normal, this much, right? So you can see this whole angle is I, then you have to subtract R, then you get the angle of deviation. Whole angle is I, then you have to subtract simple R, right? So here it is R minus I, here it is I minus R. You don't have to remember this, right? You have to understand this. Okay, take them down. Okay, then another situation, right? Another situation. Let's draw it somewhere here. Another thing is, so this is the interface. The light ray could be incident, perpendicular or normal to the interface. So in these cases, there's no bending of the light ray, right? So if this happens, deviation is 0. So it just goes like this, right? So we can say angle of deviation, simple D, there's no angle of deviation, right? If you draw the normal, here the incident angle is 0. If you want, you can write it. Incident angle is 0 and refracted angle also is 0, right? Always measure with the normal. Incident angle 0, refracted angle 0. And the angle of deviation also 0. There's no deviation. It just goes through like this. But if you think about velocity, it changes, right? Velocity, because this is, let's say this is rare medium, dense medium. Velocity at the rare medium is higher, but there's no bending or deviation, right? So we can say V2 is higher, V1 is lower, right? V2 is higher, V1 is lower. Even though there is no deviation of the light ray, the direction, the velocity changes, right? Velocity is higher in the rare medium. Okay. So those are the three scenarios uh, we can explain. We can explain using these three scenarios the refractive index. I know, sorry, refraction. So these are the all the ways that refraction can happen. Okay. Then write the topic. Write the topic absolute refractive index. Absolute refractive index. Absolute refractive index. Uh, under that write down. Under that write absolute refractive index. Absolute refractive index of a medium. Absolute refractive index of a medium is the refractive index. Is the refractive index of that medium. Is the refractive index of that medium relative to a vacuum. Relative to a vacuum. Okay. So you know this is sine I divided by sine R equals n. So relative to a vacuum, right? Relative to a vacuum. So relative term goes here. Relative to a vacuum, refractive index of the medium. So V means vacuum, M means medium. Don't mix these two, right? Always it is relative to the here. Relative to a vacuum. If you consider refractive index of other mediums relative to a vacuum, then such refractive indexes are called absolute refractive index, right? Usually we denote that as just simple n, right? Just simple n. So we know that in the vacuum, speed of light we denote that as c, simple c. That is the 3 times 10 to the power 8, right? Then the medium, let's say velocity is v. This is in the vacuum, this is in the medium. It goes like this, right? Numerator, denominator. Here v, m, up, down, right? So it is speed also goes like that, c divided by v. Right? C means light speed in a vacuum. So that is the highest speed, right? Light speed in a vacuum. Right. So we know that light speed in a vacuum is larger compared to any other speeds, right? Light speed in a vacuum is larger, it is 3 times 10 to the power 8. Any speed is less than that. So we can cross multiply this and we can say C divided by V is larger than 1. So what is C divided by V? C divided by V is equal to absolute refractive index. So you can see uh, absolute refractive index of any medium is larger than 1, right? Any medium means except a vacuum, right? A vacuum we don't consider medium. So refractive index of any other mediums is larger than 1. Understood? Right. Take this down. Take this down. So as I'm explaining, take notes, okay? Then let's consider a few refractive indices for materials, right? Absolute refractive indices. So write down examples. Examples. If you think about glass, what is the absolute refractive index of glass? somewhat you have to remember this, right? At least for this. For glass, refractive index is 3/2 as a fraction. For glass, 3/2. So as a decimal, you can write it as 1.2. Sorry, 1.5, right? 3/2 means 1.5. Then for water, what's the refractive index as a fraction? 4/3. So this is 1.3, right? 33. Glass 1.5, water 1.33. So when you are solving problems, you have to use either the fraction or the decimal numbers, right? Depending on that, the question would get easy or complicated. Simplification. So it is usually we use, in most of the time we use a fraction, right? It is regarding the simplification. Glass, water, then air. So what is the refractive index of air? It is actually this value, 1.0008. Okay, you can see this is closer to 1, right? So 1 is refractive index of vacuum. So air also, you can approximate that to be a vacuum, right? Depending on the question, if they don't, especially don't say that, you can say absolute refractive index of air also to be 1, which is equal to the refractive index of vacuum as well, right? So air and vacuum, we consider them to be just vacuums, right? Air also. Okay. Right. Then write this point. So whenever you have absolute refractive index, you use this equation. Light speed in vacuum divided by speed in other mediums, right? N equals C divided by V. So from this one you can see NV is equal to C. So these are important in when you are doing problems, right? That's why I'm mentioning this. NV equals C. So C is a constant. Actually, it is a universal constant, right? C. So if you can consider two cases, let's say medium 1 and medium 2. For the medium 1, it is, let's say, N1, V1, velocity is 1. You can say it is same as another one. For the second medium also, the product of absolute and velocity is always going to be equal to C. So you can use these when you are getting questions, right? N1 V1 equals, for the other medium, N2 V2. Okay. We'll do a question or example. So you have to use this one. Okay. Write down this, take down this question. Write down, if light speed in glass, if light speed in glass is 2 times 10 to the power 8 meters per second, find the light speed in water. Find the light speed in water. Okay. If light speed in glass is this much, find light speed in water. You have to use this one. Okay. Right. First write the equation, then do the substitution. Refractive index values, I gave you those, right? You can use them. Fraction values, right? Not decimals. Use the previous fraction values and substitute it and get the refractive index, I mean light speed in water. Someone tell me the answer in the chat box. Use this equation, okay? Okay, others? Any other one? So this is in medium 1, glass, right? Or it could be medium 2, it doesn't matter. So for the glass, 2 times 10 to the power 8, that is V1. N1 is glass for, what is that? 3 over 2, right? For the glass, equals, for the water, so that product is equal to this product in water. So for the water, it is 4 over 3 times speed. So this is the speed of light in water, right? So I have to simplify this. 2 cancels off. 3 goes here, 9. 4 comes here. 9 over 4 times 10 to the power 8 V2. So 9 over 4, if you want, no, you have to divide this, right? So 2.125. 10 to the power 8 meters per second. That is V2. So you can see that the light speed in water is higher than glass. Why is that? Water, it is rare medium, right? Compared to glass, water is a rare medium. So when you are doing a question, you have to think about those as well, right? Not in the exam, but so that solidifies your knowledge, right? So you can see it is a higher value, right? So inside water, speed of light is higher than, right. Then write the subtopic. Important combinations. Important combinations. Yeah. Everyone participate actively, right? Send me answers. It doesn't matter whether you got the wrong answer or not. Okay. Write down important combinations. Right. Let's try the first one. Right. First combination. So these will be useful when we are doing questions, right? So at the end of this session, you will be able to do all the past paper questions, right? So you have to carefully pay attention here, right? Right. So what is this? N1, 2. How do we say this? Refractive index of medium 2 relative to medium 1. Medium 2 relative to medium 1. That's how we say that. So we can write this like this, right? N2 divided by N1. So this is a relative refractive index. These are absolute refractive indices. So according to this one, what does it say? Refractive index of medium 2. How many times the refractive index of medium 2 compared to medium 1? Compared to or relative to medium 1. So that is what it means, right? So you have to N2 divided by N1 there. So this is the first thing, right? You can write this with me. Okay. So how do we prove this? So I'm going to prove this, right? So you should be also able to prove these, right? These are not complicated proofs, right? So N1, 2. How do you write this? 1, 2 means these could be any two mediums. V1 divided by V2, right? 1, 2. 1 is here, 2 is here. So is numerator and denominator, right? V1 divided by V2. 1, 2. Velocity goes like that. 1, 2. Here also 1, 2. So let's say this is the first equation. Then I'll write N2 divided by N1. So these are absolute refractive indices, right? N2 means, so for absolute refractive index, you get C divided by V, right? N equals C divided by V. For the second medium, for the N2, you can write it like this, C divided by V2. Instead of N2, you can write C divided by V2. Instead of N1, you can write C divided by V1. Okay, if you don't understand, tell me. C divided by V2. For the N1, C divided by V1, right? Then CC cancels off. Then what do you get? So this is inverse, right? So V goes up, V2 goes down. So V1 divided by V2. So this is the second equation. So you can see this side and this sides, they are the same. So you can see 1 equals 2. So what do you get? N1, 2 means what? N2 divided by N1. You have to remember this, right? You can use this at once. This is a standard equation, okay? So that's why you have to draw a margin here. So these, you can use this at once. 1, 2 is equal to N2 divided by N1. This equation you can only apply when this N is absolute refractive index, right? This should be vacuum speed. For other indexes, you have to use normal speeds, V1 and V2. So that's the difference between those. I think done, right? Okay. Then write down a second combination. This also you can apply. N12 is equal to 1 over N21. You can change the mediums and write it under 1. Right. So if I take this side, you can write it like this. N12 means what? V1 divided by V2. So that's the first equation. Then the second one, I'll simplify this one. Oh, I'll write N21. N21 is what? V2 divided by V1, right? V2 divided by V1. If it is 2, 1, it should be V2 divided by V1. V2 divided by V1, you can write it like this. V1 divided by V2. Get it? You can write V2 here, but you have to write it under 1, right? So what is V1 divided by V2? It is 1 N2, right? I'm doing these proofs to familiarize these things with you, right? You can prove these any way you want, but just to family, otherwise you get confused there, right? Okay, done. Okay, so to practice these two, we'll do a question. Write down, find refractive index, find refractive index of glass, find refractive index of glass relative to water. Find refractive index of glass relative to water. Within brackets, right? So glass, refractive index of glass relative to water, right? This is how you write it. So this is within brackets. And refractive index of water, refractive index of water relative to glass, refractive index of water relative to glass. Within brackets, right? GW. Okay. So I have to use previous two equations, two combinations. First, just find this one. Absolute refractive index are given, right? These are relative refractive indices. You can use them and tell me the answer. For the first one, tell me the answer. So NWG, how do you write that? Relative to water, right? So water goes here. Absolute refractive index. How many times compared to water? The refractive index of glass. So using this one, you can find that. So what is this? 3 over 2, right? NW means 4 over 3. So this goes up. This is the main division. This goes up. It flips, right? 3 over 4. So this is 9 over 8. So 9 over 8 is what? Refractive index of glass relative to water. Okay? Yeah, 9 over 8. Then what they ask is other one, right? So other one should be what? Water relative to glass. Water relative to glass. So you can write this like this, right? N WG. You can change the positions and write it under 1. So it should be the reciprocal of this, right? So it should be what? 8 over 9. Yeah, 8 over 9. Right. Then, so it is a second combination. We discussed up to the second combination. The another one you can use is, let's say third one. Third one, you can write like this: 1, 2 times n, 2, 3. There's a pattern. You have to understand, recognize that. N, 3, 1. Right? So you can see here 2, 2. Here 3, 3. Okay? So this thing is equal to 1. If you want, you can use this as well at once. You can see here 2, here 2, here 3, here 3. These kind like cancels off. Then it becomes n 1 to 1. 1 to 1 means you get n 1, 1. There are many ways you can derive this. Okay. I'll use this one. You can derive this using speeds as well. I'll derive this using refractive indices, right? Okay, because you have to get familiar with that more. 1, 2. How do you write the refractive index? Absolute, in terms of absolute. This is index of 2 relative to 1. So I have to divide by 1. Got it? Divide by 1. This one, relative to 2. Divide by 2. N3, right? Divide by 2. Here, relative to 3. Medium 1. Divide by 3. N1 goes here. So you can see what? N3, N3, N2, N2 cancels off. N1, N1 cancels off. Becomes 1. So that way you can derive that. Or else, you can use speeds, right? Speeds in different mediums. You can use speeds in different mediums and derive the same thing. If you want, I can show you. But speeds goes like this, right? 1, 2, numerator, denominator. For the absolute refractive index, it is other way. For this one, what? V1, V2. Here, V2, V3. Here, V3, V1. So you can see these cancels off, right? For speeds, it is easier. We can write it for speeds. Right. Then the fourth combination, you can use, write that down, n sine theta equals k. This is the third combination, right? N sine theta equals k. So this is one of the most useful one, right? N sine theta equals k. The meaning of that is, for a given medium, for one medium, refractive index, absolute refractive index, and the sine value of that angle there inside that medium is a constant, right? Okay, we see how to derive this. Deriving this, it is just to familiarize with you the theories, right? In the exam, they won't ask you to derive this. You can use this at once. but these are not complicated derivations, right? Okay, for this one I'll just draw something like this I. So this is the ray diagram. Okay, medium 1, medium 2, incident angle, refracted angle. So this is what we need to derive. Absolute refractive index, let's say here absolute refractive index N1, here absolute refractive N2, right? So you can write Snell's law here, right? Sin I divided by sin R. Sin I divided by sin R. Sin I divided by sin R is equal to what? You can write like this 1, because I is here, it goes to the same medium, right? If I is here, you write it here 1 like this. If it is sin R, you go to the medium 2, R2. Okay, you have to clearly understand that difference, right? Otherwise you would mix that up, right? Sin I1, sin R2 into I1 R2, right? But when you are writing, so this is relative refractive index, but when you are writing this in terms of absolute refractive index, you go for the other way, right? Relative to 1 means you have to divide by 1, absolute refractive index. So when you are writing that, it flips, right? N2 divided by N1. Here it is 1, 2, sin I, sin R. But for the absolute refractive index, it is N2 divided by N1. Okay? Right. So here we have sin I divided by sin R is equal to what? N2 divided by N1. Then you cross multiply. N1 sin I equals N2 sin R. What is N1 sin I? Here, right? N1 sin I equals N2 sin R. What does it mean? For any number of mediums, this product, absolute refractive index times sine value of the angle there, is a constant, right? You can use this at once. When you use this is less confusing, right? So I recommend you use this always. You need to be able to do this as well, but this one is less confusing, right? Because just n1 at the same side, n1 sine I multiplied by n2 sine R. So those are the same sides. N1 sine I equals n2 sine R, right? So if you use this, it is easier to use, right? Without any confusions, right? Take that down. If you are done, thumbs up, okay? Okay, so to practice this, we'll do a question, okay? These questions are just to explain the theory, okay? Right, write down, put a Q there. Write down, on a water glass surface, sorry, on a water glass interface, on a water glass interface, incident angle, incident angle from water medium, from water medium is 30 degrees, is 30 degrees. Find its refracted angle, find its refracted angle and angle of deviation, refracted angle and angle of deviation. So you have to use the last combination, right, to find that. Find its refracted angle and angle of deviation. If it is confusing, you can draw this. So let's say this is water, this is glass. It doesn't matter, you can draw it here as well, right? Water, glass, it doesn't matter if you flip this, as long as you correctly substitute. Here water, here glass, then the angle of incidence is 30 degrees from water side, right? That is what they say. Then for the glass, it is dense, so it bends like this. So what they ask is simple r and angle of deviation, right? First find simple r using the last combination, right? So for water, you know, it is 4 over 3. For glass, it is 3 over 2, right? Absolute indexes. You will have to use sine, right? Sine table. Times 11, right? Close to 11, I think. Okay, do this now, right? You need to pay the full attention, so you can do all the questions, okay, under refraction, the past paper questions, okay. If you don't understand, didn't get this correctly, then the remaining part of optics also will be very hard, right? Okay, let's see. So how do you do this? Right. So this is the equation. Absolute refractive index, water, sine, let's say I, equals Ng sine R, right? Nw sine I, sine 30, equals Ng sine R. So simple R is what we need to find. So Nw is what? 4 over 3, right? Water. Sine 30 equals Ng is 3 over 2 sine R. Right. So sine 30 is what? Value sine 30? 1 over 2, okay? By now you should know that. 1 over 2 equals 3 over 2 sine r. Okay, if you don't understand, tell me. Okay, so we can say this 2 goes up, cancels. Then this, you can cross multiply this becomes 4, this goes here. 4, this equal sign, 4 divided by 9. So sin r is equal to 4 divided by 9. Okay, up to here it is a simple calculation. After that, you should be able to find simple r. You should know how to find that. So simple r is what? Sine inverse 4 divided by 9. So you need to find the inverse value of, inverse value of sine 4 divided by 9. Okay. So for this one, what do you have to do? You need to refer the sine table, right? Sine table. There's no any other way. You need to have that practice. Okay. You need to practice that. In the exam, they ask you to find these values. Okay. Not in MCQs, but in like essay questions or structured essay questions. They could ask. So you have to convert this into a decimal, right? 4 over 9. So how many? 0 point. 4 doesn't have 9. 0. 40 has 4. 4 nines. 4 is remaining. 36. 4 is remaining. Something like this, right? Sine inverse 0.4444, something like that. So you need to find the inverse value of this from the sine table. So what do? So you have this table, you need to find this value from here, 4 something. Then from here you can find the degree. Here that value is 26 degrees. Okay. Perpendicular, if you look perpendicular, that value is 23. So this is minute, 23 minutes, 26 degrees and 23 minutes. Got it? So that is how you go for the inverse. So to find the value of that one, it goes like that. To find the inverse, you need to locate the value from the table and then how many degrees, how many minutes. Okay. Right. So the value here for the refract angle 26, 23 minutes. 26 degrees, 23 minutes. Okay. Refer the sine table. Okay. You have to practice that. So when we are discussing prisms, this will often we have to use this. Okay. Sine table. If you have a problem, let me know. Okay, take it down. If you're done, thumbs up. Others, if you're done, thumbs up. Okay. Right. I think how to refer the table. You understand that, right? Okay. So we found angle of refraction, simple r. Then then we need to find what? Angle of deviation. That is simple d. What is that? You know that this value is 30 degrees, right? This value is 30 degrees. See that? This is simple d. So 30 minus r is d. 30 degrees minus r. R is 26, 23 minutes. 26 degrees, 23 minutes. Okay. So how do we do this simplification? Here I will discuss how to do these calculations, right? Because I need to use them in when we are discussing prisms, okay? Right. So how do we subtract this 30 from 26, 3 minutes? So you can write this 30 degrees like this, right? You can write it as 29 degrees and a 1 minute. You can put 1 minute here. So 1 minute is a 60. I mean 1 degree is a 60 minutes. You can write 30 degrees like this. 29 minutes, 60 degrees. This also is 30 degrees, okay? Then subtract 7. 5 minus 2, it is 3. So 37 minutes. Then 3 degrees, right? So the angle of deviation, it is a small angle for this quest, right? 3 degrees and 37 minutes, right? If you didn't understand, tell me, right? I'm not going to again discuss this when you are doing prisms. So when you are doing prisms, this should be clear, right? Right. So that is, now we have covered that part, right? So this type of calculation, you have to practice these. Okay. Then write the topic, subtopic, refraction through refraction through parallel slabs. Refraction through parallel slabs of mediums. That's a subtopic, okay? Refraction through parallel slabs. Slabs means, slabs, right? Slabs of mediums. Okay, so we have discussed all the basics of refraction, right? Then we have to apply those and derive some of the applications. So the next part is that one, right? Okay. So you have to know these before, because these will be useful when it comes to MCQs, right? So you have to know these facts. Okay. Let's say, so these are parallel slabs, okay? Here you have a, this could be air, this could be water, then another medium, N2. Then again same medium. The mediums here and here same, right? Here you have something else, N2, right? So let's see what happens when a light ray enters. So there are three mediums actually, but these two mediums are the same, right? Light ray enters like this. Let's say with the incident angle theta 1. Then it bends. Let's say now the angle is theta 2. Since these two are parallel, you can see this if this is theta 2, this also should be theta 2. You know? Right. Then what happens? Then let's say this is a rare medium. It doesn't matter. Then it bends like this. Let's say this angle is theta 3. Okay. I think you understand that. Light enters from the same medium and emerges to the same medium as well. Right. There could be number of slabs here. So here what I'm going to prove is, even though how many slabs here, if it enters the same medium and leaves from the same medium, this ray and this ray, they are parallel, right? They are parallel. It doesn't matter how many mediums here, as long as they are parallel slabs. This ray also is going to be parallel, right? Incident and emergent ray, those are parallel. So let's prove that, right? Just apply Snell's law to this point. let's say P, then to point Q. So what I have to do is, you have to prove that theta 1 is equal to theta 3. So that is what you have to prove, right? Okay. So if you apply to P, Snell's law, n1 sine theta 1, n1 sine theta 1 equals what? n2 sine theta 2. n2 sine theta 2, right? n2, this angle. Then to Q, to this point, what do you have? n2 sine theta 2. n2 sine theta 2 equals to what? n1 sine theta 3. So you can see this term and this term, they are the same terms, right? So what does it say? This term and this term should be equal. So n1 sine theta 1 equals n1 sine theta 3. So n1 cancels off. Sine theta 1 equals sine theta 3. So from this one you can see theta 1 is equal to theta 3. Understood? Take it down. It doesn't matter, there can be number of slabs, right? As long as these two mediums are the same and they are parallel, slabs are parallel, this ray and emergent ray is going to be parallel, right? If you're done, thumbs up. Everyone? Others done? Okay. Under this, write down. Under this, write down. Therefore, incident ray is parallel to incident ray is parallel to emergent ray. Incident ray is parallel to emergent ray within brackets, right? uh, zero deviation of angle. Zero deviation of angle. Then to the same line, right? But there is a partial displacement. But there is a partial displacement. but there is a partial displacement. So what is partial displacement? So we know that this one and this one parallel, right? If you extend this, it comes like this, right? So you can see there's a displacement here. This is what we call partial displacement. The ray should emerges from here, but it has emerged, it has moved backwards, right? So this is what we call partial displacement. Okay, right. Okay, so the next phenomena that we have talked about is apparent depth, right? So they have asked many questions, I mean MCQs regarding this one, right? Okay, write the subtopic apparent depth. Apparent depth. Okay, so so let's say there's a beaker or a vessel that contains water. So you don't see that when you look the depth, I mean bottom of that, what you see is that bottom has lifted upwards, right? You don't see the actual depth. You always see a less depth, right? So the depth you see is what we call apparent depth. Okay. So when you look through like a water vessel or any content, so the bottom is looks like it has shifted upwards, right? Okay. So when you look the bottom of a pond, the depth of that pond is not the actual depth. What you see is apparent depth. It is always less, right? Understood? So due to refraction of light, that happens, right? The bottom of the that pond looks shifted upwards, right? So you always see a false depth, right? So you have to be careful there, right? So let's see how that happens. Okay, right. Let's say this is the interface, right? For the simplicity, I am considering this to be, we have air, right? So the refractive index of air is 1, right? So it is, we approximate it to be a vacuum. So for the air, refractive index is 1. And let's say refractive index of the medium, this can be water or can be glass or anything else. Uh, so this is refractive index is simple n, right? Any transparent medium. Let's say you have the object here. You have an object here. The object is actually here, right? Object is actually here. But if you look from somewhere here, you don't see the real position of the object. Okay? So what you see is image of this object, not the object. Image of the object is what you see, right? So by this ray diagram, you are going to find the position of the image. So you need to know, to find the position of an image, you need to have at least two rays, right? Okay, I can draw one ray. So from this object, rays goes everywhere, right? Like 360 degrees. There are infinite number of rays going out of this object. Okay, but you need only two rays to find the position of the image. I can draw this one, right? I can choose this ray. I can choose a ray that goes perpendicular to the interface. Then perpendicular. Because I chose this because I know the direction that it goes after refraction. It doesn't bend, right? That's why I get this ray. Then I'll draw another ray. Let's say like this. Draw the normal. You know that this is a rare medium. This is a rare medium. So in a rare medium, what happens? The light ray bends away from the normal, away from the normal, right? Then you have to extend this till these two rays meet. So this is the final ray, right? Final ray. This is the another final ray. So you can see from here you cannot meet this ray, right? So you extend this backwards. Here you can see these two rays intersects. That is where the image of O is going to be. So here the image is created. I. Understood? Okay. Right. Let's say this point A and this point B. This point. This AO is what we call true depth. Actually, the object is here, right? True depth. This AI is what? This is not a real depth, right? This is the distance to the image from the interface. So AI is what we call apparent depth. This is the depth we see, apparent to us. So that is AI. Apparent depth. True depth or real depth? Apparent depth. Okay, draw that one. When you are drawing, you have to understand, right, what is happening, right? Understand now. You won't have another time to, with the workload, you won't have another time, right, to understand these things. You have to understand this now, right? Okay, thumbs up if you're done. Thumbs up if you're done, right? Okay. Right. Then, to this position, I'm going to apply a Snell's law. Snell's law, right? Okay. So this ray, what is this angle? This is incident ray and angle is I, right? Then this is R, right? Refracted angle, incident angle. Got it? Then we can say if this is I, these are parallel, right? These two lines parallel. If this is I, this also should be I. I, Z, right? Then you have F here. This one, these two are parallel. If this is R here, this also should be R. R, R. This is the same line. Okay. Now we have I and R. If we apply Snell's law here, you know the refractive index, I took it as simple n of this medium. N times sine I. N times sine I equals, this is AR, so refractive index I took it as 1 approximately, times sine R. So here we have N sine I equals sine R. Okay. The thing is, even though we draw these like very large angles, these angles are actually very small, right? Very small, these angles. Why is that? These rays has to go through the pupil here, right? If I draw that very thin, then this image is not clear, right? All these rays has to go this through the pupil here, right? So these angles are very small, I and R, you know. I, R, those are very actually closer to 0. You know that when in that case, sine values can be written as tan values for small angles, right? I think you have learned those earlier when you are doing like simple pendulum. So if these are very small, you can write n tan I equals tan R. Sine values can be written as tan values if very for small angles. Okay, right. Now let's see what is tan I. Consider this triangle. What is tan I? AB divided by AO. Opposite divided by adjacent. Tan R. Consider this triangle. ABI. Opposite AB divided by adjacent. AB divided by AI. If you don't understand, tell me, right? Then AB cancels off. N is what? AO divided by AI. AO divided by AI. AO divided by AI. Right? So what is AO? AO means real depth or true depth. Let's say real depth. Doesn't matter. AI means apparent depth. So this is the main equation. N equals real depth divided by apparent depth. Take it down. It is always real depth divided by apparent depth, right? Real divided by apparent. Then it is equal to N. This is an absolute refractive index if it is air or vacuum, right? For others as well, you can use this. Okay, take it down. Right? Right. Under this one, right? This simple n, right? Write down uh, simple n, simple n is the refractive index, is the refractive index of the medium, of the medium relative to, relative to the medium, relative to the medium that the I means this one, right? That the I is in, that the I is in. Right? So that simple n is a relative one, but for any cases, right? For any cases, you can consider when you get a question, always it is relative to the medium which the I is placed. You will see when we are doing questions. Okay, right? We'll do a question to practice this. Write down Q. Water is filled into a beaker. Water is filled into a beaker to a depth 12 centimeters. To a depth 12 centimeters. When look from above, when look from above, when look from above, find the apparent depth of water level, apparent depth of water level. You can use the last equation at once and find the value apparent depth. So what's the value? Send me the value. You can directly use the last equation, right? No, real depth is 12, right? Real depth is 12. Okay, simple n equals real depth divided by apparent depth. Apparent depth is what they ask. So n is what? It is the water, right? So n is just 4/3. Real depth is given. It is 12. So what they ask is apparent depth. Okay, apparent depth equals 12 times 3/4. 3/4. 3. So 3 times 3, that is 9. Okay. Should be 9 centimeters. Because it has to lift upwards, right? So let's say if you have a beaker, if you want, you can draw this from a side. Water is actually filled to a 12 centimeter level, right? You are observing from the above, right? So the relative to the air, right? I is in air, so relative to the air, okay, relative to air, refractive index of water, relative to air. So you look that, but you see this has 9 centimeters. Can you see there? It has shifted 3 centimeters. So the apparent depth is 9 centimeters. Understood? If you want, you can draw this. So always remember, okay, always remember to take relative to the medium which the eye is in, right? So it is then it is going to be valid for any case. But this thing is always real divided by apparent, right? Real divided by apparent, always. Right. To further clarify, we'll do one more question regarding this. Write down Q2. Q2. Write down find apparent positions apparent positions apparent positions of the bird and the fish. The bird and the fish. Okay. The bird and the fish. So so these are real positions. Okay. Real positions. 54 centimeters. There's a bird here. These are real positions, right? Bird is here. Then there's a fish. So all the measurements are taken from the interface. Okay. This is 32 centimeters. Here you have the fish. These are real positions. Okay. So what they ask here is apparent positions. So how does the bird see the fish? Bird does not see the fish here. It sees the fish has shifted upwards, right? That is how the bird sees the fish. Not us, right? These two ones. So the eye is in air now. Eye is in air, right? Because we are thinking about bird. Now the fish is here. Let's say depth is x. Okay. So this is regarding how the bird sees the fish. Another case. Fish sees the bird. Actually, fish sees the bird like this, right? Above. Right above, right? Like this. Let's say that everything is measured from the interface from at a distance y. So these are apparent positions, right? Apparent positions. How the bird sees and how the fish sees. This is I. This is also I. These two are images actually. This is the image of the fish, image of the bird. This is not how we see, right? This is how bird sees the fish, and this is how fish sees the bird. Fish sees bird above that, right? So what you have to do is just find x and y. Okay, right. Let's find x first. So what's the equation? So this is water 4/3. This is the equation. Real divided by apparent depth. How do we write the refractive index? Relative to air. Refractive index of water. So this is absolute refractive index, right? Why did I take air here? Because relative to the place which you place the eye, where you place the eye. Yeah, at this point, eye is in the air, right? The eye of the bird. Understood? Relative to air. So this refractive index, we know that it is 4/3 actually. Just absolute refractive index, 4/3. Okay, real depth is what? You measure the depth from the interface, right? Not from here, from the interface. So depth is at the fish at a depth 32 centimeters. That is the real depth. Apparent depth is simple x. Okay. Now cross multiply 1, 8, 24. So x is 24. Can you see that? It is less than 32, right? Now the meaning of that fish has shifted upwards. 24 centimeters. Okay. First take it down and let me know. Right. Then we need to find y, right? When you look a rarer medium from a denser medium, you see that away, right? Let's see n. So now where's the eye? Now you are thinking about the how the fish sees. Now you are thinking about the eye of the fish, right? Now eye is in water. So relative to water, refractive index of air. So this is equal to real divided by apparent, right? This doesn't change. It is always real over apparent, but now it is WA. Always you have to consider the I here, right? I, right? So we know that you can write this like this, right? 1 over n AW. Remember the earlier ones? You can write it 1 over, you can change the positions. Real divided by apparent. So what is this? AW means 4/3 equals real depth. Real depth of the bird measured from the interface, bird is at a 54 centimeter. Apparent depth of the bird is y, right? So this is 3/4 equals 54/y. you can divide by 3 both sides. 18. 18 times 4, 36, 72. Get it? So it is more than that, right? More than, the value is 72 centimeters. Take it down. If you don't understand, tell me. The thing is, you have to understand whether to write it at the numerator or denominator, right? Remaining is easy. If you mix that up, then you will get a completely different answer, right? You have to make your own way to identify that, whether to write it at the denominator or numerator. It is always real divided by apparent, but here always relative to the medium, the I, medium of the I, right? Understood? Right. If you have any doubts, just clear that out, right? Because without this, it is very hard to understand the remaining parts. Okay. Okay. Then we have to talk about another one, that is apparent displacement, right? So we talked about apparent depth. It is measured from the interface, apparent depth, then apparent displacement, right? Write down the topic, apparent displacement. Apparent displacement. So this is similar to the previous one, but it is how much the shift upwards. That is what we are talking about here. Apparent displacement, within brackets write simple d. Apparent displacement within brackets simple d. Right. So here the interface, right? You have the object really here, real position of the object. Then you draw this ray perpendicular, right? Why do we get that? Because after refraction we know the direction that it goes, right? So you can draw that. Then one more ray we need to find the position of the image of O. If this is a rare medium, then it bends away. Then extend this till it meets these two rays, it meets here. So the image of O is formed here, above, right? This is what we call D. It is shifted by D amount, which is called apparent displacement. Apparent displacement, not depth, right? Displacement. Then, this at the previous theory we discussed this to be real depth, but here we say this to be thickness, right? Usually we are using this to find thickness of a glass slab when you place, those are the practical applications, right? When you place glass slab on a newspaper or something, you can see that letters are shifted up, right? So in that case, we say that it is to be a thickness. That's why we say this real depth actually, but in this case we say that uh, thickness. Thickness. Usually we put use this to for glass slabs. That's why, right? But the same thing, okay? Actually, this is real depth. Okay. So from the previous theory, we knew that we derive simple n, right? So I is here relative to the this medium, this one. Let's say it is air for the simplicity, and n here, right? So it is n divided by 1 is n equals real divided by apparent. Okay, real depth divided by apparent depth. So I have to write this in terms of T and D. So what is the real depth? This much is the real depth. That is thickness, real depth. Apparent depth, this much, right? What is that? T minus D. This is T minus D. T minus D is equal to N. So here as well N is defined similarly, right? Because it is the same theory, but for the same thing we have different forms, right? Okay, let's cross multiply. Tn minus dn, Tn minus dn equals T. Put T here, Tn minus, get this T to here, put Dn to there. Then divide the whole thing by simple N. I need an equation for D, right? So Tn minus T divided by N. So you get D equals, divide it, T minus T divided by N. T minus T divided by N. Then take T out, 1 minus 1 over N. This equation you need to remember. You have to remember this, right? T times 1 minus 1 over N. This one you need to remember this. Okay. Take it down. Right. Okay, let's apply this to a question. Write down Q. Write down a glass cube. A glass cube with thickness. A glass cube with thickness 4.8 centimeters. 4.8 centimeters is placed on a newspaper. On a newspaper. How much is the shift of letters when look from above, when look from above. Okay, okay, apply that. First write the equation, then substitute. So you're finding the shift of letters. So you can observe actually in real life, right? Uh, Actually, if you can measure the thickness of those glass slabs, you can find the how much is the shift. So you see the letters somewhere here. Okay, quickly find that. Shift means simple D, right? Apparent displacement. Use the fractions, right? When you're substituting. So it should be 3 over 2. Okay, let's see. So thickness is 4.8. 1 minus 1 over 3 over 2. 4.8. 1 minus 3, 1 over 3 over 2 means what? 2 over 3, right? 4.8 times 1 minus 2 over 3 means 1 over 3. Yeah, 1.6. 1.6 centimeters. Correct. 1.6 centimeters. Okay. Right. So that amount, the letters shift upwards, right? Then if you want, you can find the apparent depth of letters. So all you have to do is 4.8 minus 1.6. That is the apparent depth of letters. This is how much shifted up the letters. Right. So under this one, under apparent displacement, there's an important point that you need to know. Uh, put a point and write down proving that apparent displacement proving that apparent displacement is independent of position of the object. Position of the object. Position of the object. Okay. Listen carefully, right? This is very important. Many don't understand that this well, right? Okay. So let's say this is the glass slab, right? Glass slab. In this case, I'm not going to place it here, right at the bottom. I'm going to put it below that, below somewhere at the bottom, right? Object. Okay. Both side it is air. I'm not putting it here, somewhere here, right? Then I'm going to draw the ray diagram to find the position of the image. Then this ray goes like this. Since it is glass, it bends towards the normal. Then again here, again it is air. You know that this ray and that ray, they are parallel, right? Earlier we learned that. This one and this one parallel. Earlier we learned, right? So I is here. So the final we always have to consider the final ray. That is what creates the image, right? Then we extend the final ray to here. Okay. So let's say this is O, then O dash. Let's say this is I. This is where the image is formed. And let's say this is I dash. Okay. So from this one you can see OI and O dash I dash. They are parallel. See that? These are perpendicular lines, right? So OI and O dash I dash parallel. Another one is what? Earlier we learned this ray and this ray parallel, right? So we can say O dash and I dash parallel. I dash parallel. So what does this prove? If you have these to be parallel, then we can say I dash O dash is parallelogram, right? So it is geometry, parallelogram. So we can say this to be a parallelogram. Got it? Right. So what is this? This is apparent displacement. If this is a parallelogram, this length and this length equal, right? Right? What does it say? Even though the object is here, you will get the same displacement, apparent displacement. Even though object is here, regardless of the position of the object, apparent displacement will be the same. This, see, this value didn't change. This is d here, this also is d here. Understand? Okay, take it down. I think you understand that, right? If you don't, let me know. So thumbs up if you're done. Right. Uh, at least you need to remember this theory, fact, right? It regardless of the you place the object, the apparent displacement is same, right? It will be useful when you are doing problems. Okay. Okay. Then this next point, put a point. Write down when there are several when there are several parallel mediums. When there are several parallel mediums. Okay. It is like this. Put a comma. Let's say this is N3 medium, N2 medium, N1. You can draw it with me. N1, 2, 3. And thicknesses are T3, T2, T1. Here you have AR, right? So the refractive index is 1. Then you look from above. Then you place an object here. There are 3 mediums. So in this case, what do you do? You can derive this, but I'm not going to derive this, right? You can directly use this one. So this makes a shift. Other one also makes a shift, right? Other one also makes a shift. There are 3 mediums, all 3 makes a shift. Then you just have to add all those. Shift caused by this medium plus shift caused by this medium plus shift caused by third medium, right? Then you just add all those. You can derive this actually, right? It is not necessary. Okay, for D1, how can I write it? For D1, similar to the equation, T1 1 over N1 plus D2, T2 1 over 1 N2 plus T3 N3. Understood? So this is how you find the total displacement. Take it down. If you don't understand this, tell me, right? So thumbs up if you're done. Okay. 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 So under refraction, then we have to talk about total interreflection and critical angle, right? We'll quickly do that. Okay. Write down the topic. Total internal reflection, not refraction, right? Reflection. Total internal reflection. right? So for this one, this rare, and you have dense. Okay. In order for this to happen, the ray always goes from dense medium to rare medium, right? Otherwise, this doesn't happen. From a rare medium to a denser medium, there's no total reflection. Always ray should goes from dense to a rare in order for this to happen, right? Okay. So as usual, I can put the object. So from the object to all the directions, rays are going, propagating, right? From the object. But we are only choosing the required rays to explain this. So as usual, I'll draw this ray perpendicular to the surface. Okay. Then another ray. Let's say it emerges. This is rare medium, so it moves away, right? Like this. Moves like this. Then I'll draw one more. So you can see here the incident angle is larger, right? Larger. So you can draw any number of rays, but as this incident point moves to here, incident angle is getting larger, right? I2 is larger. So when I2 is larger, refracted angle also has to increase. So this increase. So can you see this refracted angle is bending towards the surface, right? There's a special incident ray that the refracted ray goes right along the interface. Then at that point, we call the incident angle to be capital C. That is the critical angle, right? So any ray being incident beyond this critical angle, critical point, gets totally reflected into the same medium. Doesn't have to be here, right? Right after this, it gets totally reflected. So we know that when it is reflection, at the reflection angles are incident and reflected same, equal, right? So there's 100% reflection. Okay. So this is what we call total internal. Why internal? To the same medium. Internal reflection. Other rays, right? These rays, partial reflection. You know that I can draw it like this. It is about 20%. It always happens 20% reflection and 80% refraction. But only for this one, there's 100% reflection total, right? So these are partial reflection. This is total internal reflection. Okay, take it down. So from this diagram, I'm not going to explain this. I think you can understand that, right? From this diagram. So any ray after this gets a total internal reflection, right? Any ray to this side gets only a partial reflection and a refraction. After this point, there's no refraction, only a reflection, 100%. Thumbs up if you're done. Hello? Oh, තාම ඉවර නෑ බා. තව විනාඩි 10ක් විතර. ආ. Right? Okay. Then we have to talk about critical angle, right? Write down critical angle within brackets capital C. Okay. So right. So this could be rare medium or this could be air, right? This is another other dense medium. So a ray comes from dense medium and goes through here. This is when the critical angle happens, causes, right? For a ray like this. So we need an equation for the critical angle. So just put Snell's law, n times sine c equals, this is 1, right? Refractive index 1. 1 times sine, now the refracted angle is 90. Sine 90 is 1. So we have sine c equals 1 over n. So c is equal to sine inverse 1 over n. Right? So sine c equals 1 over n. Usually this n is rare medium, right? Here rare medium relative to rare medium. Not usually, it is always rare medium, other medium, right? Actually this is derived for the air, but for any two mediums we can derive that. But this has to be dense, this has to be rare, otherwise critical angle cannot happen, right? Relative to rare medium, this medium. Okay. Okay, take it down. Thumbs up if you're done, right? Okay. Then we'll do a question. Write down Q, put Q, then write find critical angles, find critical angles for for water, air, and water, air, comma, glass, air, comma, water, glass. Yeah, so interfaces, interfaces. Okay, let's find for water, air first. So we know that sine C is equal to 1 over n, right? So rare, medium, medium. So when you think about water and air, what is the rare medium? Air, right? So relative to air, density of water, I mean index of water. So here you have air and here you have water. Always it is the rare medium here, right? Okay. Okay. So it is actually the absolute refractive index of water. Okay. So this is flips 304, 0.75. Then sine inverse 0.75. Okay. So this is the critical angle for water air surface. So if you exceed this angle, then total internal reflection occurs. If the incident is less than this angle, then refraction, right? Find this value, right? You have to practice this for now just to check. I'll put the value. You have to find, you should be able to find this in the table, right? Take it down. Then glass air. Sine C equals 1 over n. Here, rare medium is air and denser medium glass. This also is absolute refractive index, 3 over 2. So 2 over 3. So sine inverse 2 over 3 means 0.666 something. Okay. So find these values at home, okay. You need to do these questions again to practice, otherwise that prism part will be difficult, right? So here you can see this value is less. Critical angle is less here because for glass, uh, critical angle is less, right? Because for glass, n is higher, right? You know that uh, because sine c is 1 over n. If n is higher, c should be less. That's why, right? You have to compare that. Critical angle is less for glass because why? Absolute refractive index is higher for glass compared to water. Okay? These two are easy actually. Important one is this one. Water glass. The reason I am doing this question is this will be useful to understand a practical in the future, right? Regarding prisms actually. That's why I am doing this question especially. Right. For this one, science is what? Rare and dense. So when you think about water and glass, what is rare? For water value is 1.3. Glass it is 1.5. So water is rare medium, right? Understand? Water is the rare medium. So relative to water, it should be relative to water index of glass. Okay. So what do you have? Relative to water. So Ng divided by Nw. Ng divided by Nw. Nw goes up, Ng comes down. So Nw is 4 over 3, Ng is 3 over 2. So it should be 8 over 9. 8 over 9. So sine C is 8 over 9, right? So C is what you need to find. Sine inverse 8 over 9. What do you get? 0.889, right? You have to do these questions again, okay? So the approximate value for you to check that 62 degrees and 44 minutes. That is the critical angle for glass water surface. If there's a glass and there's a water layer, that is the critical angle. If you're done, thumbs up. Right? Okay. Write down this one, not topic, just a sentence. According to the principle of reversibility, principle of reversibility of light, comma, given that incident angle is 90 degrees, incident angle is 90 degrees from the rear, 90 degrees from the rear medium, rear medium side, the ray, the ray enters the dense medium, the ray enters the dense medium at critical angle, at critical angle, okay, at critical angle, right? Okay, this is what it means, right? This will be useful in MCQs. That's why I'm giving you this, right? So there's a principle of reversibility in light. So what is that? So we know that, let's say this is dense and this is rare. So we know that when it is incident from dense medium to a rare medium, critical angle, emerge refracted angle is 90 degrees. Okay, that we know. So what is reversibility of light? Underline reversibility of light, right? In the sentence, reversibility of light. This will be useful for the remaining parts as well. Reversibility means, let's say now the ray is sent like this. If you send the light ray to opposite other direction, then it will follow the same path, right? It's like this. If you send the light ray like this, then it will follow the same path, right? It makes sense, okay? If it goes like this, and if you reverse the light ray, it will follow the same path. That is what we call reversibility of light. Just learn that here, okay? Just draw them. This is rare medium and it is dense medium, okay? Rare and dense medium. Thumbs up if you're done. Done? Okay. So that is all regarding refraction, right? This is a large part, right? This is like this has so many facts, but somehow we covered that, okay, within like more than 2.5 hours. Uh, anyway, so since we have covered all the theory parts and all the details on this refraction part, now you can practice trying. You have to try doing the MCQs, right, from 1992 to 2024. Okay. Then I'll put a explanation on these MCQs. Okay. Then you will have a perfect understanding of refraction. So once you get that, then you will be able to do any questions, right? And also this puts the foundation for the remaining optics. Without doing this, you will not understand optics, right? So first, so the same time next week, by that time, you just have to finish all these MCQs, okay? then you will have a perfect understanding of refraction part. Also, I'll put discussion on these MCQs as well, right? When you get any confusing MCQs only, you can check that MCQs, right? So all the necessary details I have discussed to do those MCQs. But you will really get the solid understanding of this only if you do this, right? Try these MCQs, then you can check the answers. Then after that, you can check the discussion video on that. Then you will have the perfect understanding of refraction part. Then we'll move on to the prism part, right? So to understand that prisms, you need to have a solid understanding of this refraction part. Okay. So how to check the value of a sine inverse value. So those mathematical forms and what is refraction and angle of deviations, all these will be useful when we are thinking about prisms.